Today we will begin talking about Taylor polynomials and Maclaurin polynomials, which are basically an extension of uh, power series and what we've been learning the last couple days. A Taylor series is a different approximation tool. So this is the first thing that we're going to do where we actually take functions that we've known and we're going to start approximating functions using polynomials, and we're going to start learning how to use calculus with that too. So uh, instead of writing all this out for you while you're watching me, I wrote all this out earlier. I wrote a function that represents this series. I wrote it out for the first 5 terms. So everything through 5 terms is in blue. And then after that in red, I decided to write what the nth term would be as we go along. So if we have f of x minus c, we have a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c squared, and so on. What happens when we take the first derivative is that this term goes away. The x minus c, the derivative of that is 1. With a sub 2 x minus c squared, we use the power rule, and that becomes 2a sub 2 and then x minus c, and so on. So it's basically just a bunch of power rules on this. It's not a very hard derivative, and you can see how that goes from there. And then when we take the second derivative, we're just taking the derivative of the first one. So a sub 1 goes away. A sub 2 times x minus c times 2, the x minus c essentially goes away. On this one, the power rule makes this a 6. Excuse me. On this term, the power rule makes that a 12, and so on and so forth. And, oh, my bad. So what we end up with here is we have all of this stuff going on in the table. And what you find is when we start taking derivatives, there's a number that starts going out in front. And if you look at the stuff that's in red, you can see probably a little bit more clearly what's happening. If I took another derivative, like the fifth derivative, this n minus 4 would get multiplied out in front, and then the new power would be an n minus 5. And so basically what you see is that the number that's out in front ends up being n factorial. So the nth derivative has n factorial times a sub n, and then there's plus a bunch of other stuff, since this is a series that goes on infinitely. So if we're looking at this particular polynomial that is defined by the sum from n equals 0 to infinity of a sub n times x minus c to the n, if we want to find this number, what is a sub n? So if we want to find a sub n, what we do is we kind of look at what is going on before everything happens. And so let's, for example, say we want to find a sub 2. Well, a sub 2 is here, here, here. And if we're looking at it, by the end of this, this just becomes 2 times a sub 2 plus a bunch of other stuff. And that's equal to the second derivative at evaluated at x minus c. And so if we're looking at what a sub 2 actually is, if I want to get that all by itself, what I would do is I'm essentially dividing by 2, or I'm dividing by n factorial, and then I can end up getting what that a sub 2 is. So a sub n ends up being the nth derivative at c over n factorial. So that's a sub n there. That's what a sub n ends up equaling. So at x minus c, if we want to find out what a sub n is, that's equal to the nth derivative evaluated at 0 over n factorial. And that's what happens when you plug in c, because c minus c is obviously 0. So you evaluate that derivative at 0 when x equals c. And so that's why, in this case, c is going to be basically our center of the polynomial in this case. So this is a general procedure for deriving a power series for a function that has derivatives of all orders. So that means that you can continually take the derivative and it never runs out of derivatives to take. Taylor series and Taylor polynomials centered at x equals c. So this is the definition. This is what a Taylor series is. So the Taylor series will be this is like an approximation of some sort of function. So we take the value of the function at c, and then we add the derivative times x minus c, evaluated at c. Then we have the value of the second derivative evaluated at c divided by 2 factorial times x minus c squared. So basically what you're doing is you're getting a value, an approximation function. And so if we have a function for something and we know its value at a certain point, we can then find what the likely, or what an approximation of a value is close to that point. And we've actually done this for a long time. That's what tangent lines always did. So this is basically an extension of tangent lines. To higher orders and higher degrees. Okay, the difference between a Taylor series and a Taylor polynomial is simple. A Taylor polynomial is a partial sum, and a Taylor series is an infinite sum. So a Taylor polynomial goes to a certain number of terms or a degree. So it might say that it's a 7th degree Taylor polynomial, or it is a Taylor polynomial with 5 terms. Whereas a Taylor series goes on indefinitely, it goes on infinitely. If the series is centered at c equals 0, then it has a special word. It's called a Maclaurin series. And both of these are named after famous old dead English mathematicians. Here are the guidelines for finding a Taylor polynomial or a Taylor series. Once again, a polynomial stops at a certain point and the series goes on infinitely. Take derivatives and evaluate those derivatives at c. So that's basically all of these things that I'm circling or underlining in red. So that's basically what those are. Notice that there is an actual function value, f of c, that we also take into account. We then write the polynomial out and we want to find a sum for it. And then we also have to determine the interval of convergence. Don't forget about the endpoints in cases where there's a specific interval. Construct a polynomial of degree 4 that emulates the behavior of f of x equals e to the x centered at x equals 0. So if we look at e to the x, this is going to be approximately f of 0. Notice that our center here is 0. So I'm replacing c with 0 in all of these, plus f prime of 0 times x minus 0. I don't have to continue writing x minus 0 all the time because this one's centered at 0. But it's not a bad habit to have to write x minus the center, because that's going to be important when it's not centered at 0, plus the second derivative at 0 times x minus 0. Sorry, I'm in the habit. Times x over 2 factorial plus the third derivative evaluated at 0. Oh, this should be a squared. My fault. Times x cubed over 3 factorial plus the fourth derivative evaluated at 0 times x to the fourth over 4 factorial. Now, we could continue adding a bunch more terms on there, but it tells us that it wants the polynomial of degree 4. So degree 4 means I'm going to stop when the degree is 4. That is different from a question that we don't have any questions like this on this worksheet, but if it asks for a polynomial with 4 terms, we would need to stop here. And the reason why we would have to stop there is all 4 of these terms actually exist. That becomes important to note because once we get to a problem like the next one, problem 2, that deals with sine, sometimes some of these terms will actually go away. All right, so if we actually evaluate these things, so e to the x is approximately, notice that this is an approximation. F of 0 is 1. That's important because that's where we're starting our approximation. So since our center is at 0, we're starting our approximation where x equals 0, and that's 1. And that's what we do whenever we did a tangent line too. Now, let's add f prime of 0. Notice that the derivative of e to the x is always e to the x. So it doesn't matter what n is for the number of derivative it is. The derivative is always e to the x. And e to the x evaluated at 0 is always 1. So 1 plus 1 times x plus 1 times x squared over 2 factorial plus 1 times x cubed over 3 factorial plus 1 times x to the fourth over 4 factorial. And again, we could keep going on and on forever about this. But I'm going to write this now kind of like you see it normally. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. This is the sum from n equals 0 to 4 of x to the n over n factorial. Now, as we make it a series, it will end up going to infinity. So this is something that we can just write down here. So e to the x is going to be equal to, now it's an approximation when we do a polynomial, but it's actually equal to the series because it goes off to infinity within its interval of convergence. So it's going to be equal to the function e to the x within the interval of convergence. And anything outside the interval of convergence, then it doesn't hold for that. So e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus all of these other terms, x to the n over n factorial. So that's the sum from n equals 0 to infinity of x to the n over n factorial. Note that this is the Maclaurin series for e to the x because the center is 0. One more thing that we might want to point out is that once again, I talked about how this is an extension of tangent lines. If you look at the first part of this, that actually is the tangent line for e to the x at or with the point 0, 1 as the point on the tangent line that you would be looking at. So you take y, which in this case is e to the x, minus, or we'll use f of x instead of y. So f of x, which in this case is e to the x, minus f of 0 equals the derivative at 0 times x minus 0. If you rearrange terms, that's exactly this. Because remember that f of x is e to the x. So in this case, this is the tangent line approximation. And that's going to be true all the time. The first 2 terms in your Taylor series, as long as they're non-zero, are tangent line approximations. Pardon part C, write the Taylor series using summation notation. Well, doggone, I already did that. So n equals 0 to infinity of x to the n over n factorial. Determine the interval of convergence for this series. So here is where we have to do some work. So the limit as n goes to infinity, I will use the ratio test because I have a factorial in it, and so that should work out pretty well. So I have x to the n plus 1 over n plus 1 factorial times the reciprocal, so n factorial over x to the n. That's the limit as n goes to infinity of x over n plus 1. And as n goes to infinity, this is always 0, regardless of whatever x is. And because that's true, since the limit of this is 0 when we do the ratio test, that means that this actually converges for all values of x. So there's nothing that x can be that can change the fact that this ratio test is actually going to make it so that the next subsequent term is not smaller than the previous one. So this works actually for negative infinity to infinity. If we look at e to the x, let's take a look at 1 and then the tangent line approximation, so 1 plus x. So if we look at the tangent line approximation, it's pretty good for a little bit of time, but it ends up diverging from the series pretty quickly. Then if we go to the second degree Taylor polynomial, so 1 plus x squared over 2, notice that it matches a little bit better. And then the more terms we get, the more this polynomial matches perfectly with e to the x for longer periods of time. And the reason why this continues to work over and over and over again for longer periods of time is because the interval of convergence ends up being negative infinity to infinity. So if we look at this, notice that the tangent line approximation of e squared is not great when it diverges from x equals 0 for the lower amounts. So like g of x, h of x, k of x here represent the first three degrees of the Taylor polynomial. So this would be the linear, this would be the quadratic, this would be the cubic approximation. But then as we get further along, more and more and more terms, we end up getting, I think q is the 7th degree Taylor polynomial here. Notice that q differs by less than 100th from the actual value. And if you continue to go more and more, it will, if you do the whole series, it will end up being exactly 7.38905 and so on. It will exactly be e squared. Now, the closer we are to the center, the sooner these values end up getting close to what happens. So e of 0.5, this is going to get really close to 1.64 really fast. And notice by k, which is our 3rd degree Taylor polynomial here, we are very close. We're within 100th already. And then once we get to our 4th degree Taylor polynomial, we are within 1,000th. And then our 6th degree Taylor polynomial, or 5th degree, I forget what it is, we are very, very, very close. 1.648, it's basically 7. And on, this gets even closer, where we have very little error. Construct a 7th degree polynomial for sine of x centered at x equals 0. So, because we're centering this at 0 again, we will have our c equals 0. And so what we're going to do is we're going to approximate sine of x. So sine of x is approximately f of 0. Sine of 0 is 0. Then we're going to add the derivative, which is cosine. Cosine evaluated at 0 is 1 times x, plus negative sine evaluated at 0 is 0 again. The third derivative is negative cosine. Negative cosine of 0 is negative 1. So negative 1 x cubed over 3 factorial, plus the fourth derivative. Notice that that's the same as the original function value at 0. So because that's true, this is another 0, plus 1 times x to the 5th over 5 factorial, plus 0, plus negative 1 x to the 7th over 7 factorial. And again, this could continue to go on. This is actually not that hard to evaluate because sine, cosine, negative cosine continues to cycle. So I can write sine of x as a 7th degree polynomial as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and that will continue to go on and on and on. We'll extend this to a Taylor series, so sine of x is equal to, within its domain, of course, or within the interval of convergence, my bad. That will be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And then we have to figure out what subsequent terms are. So that ends up being x, we'll call this 2n minus 1, I guess. That's one way to get an odd number all the time. So 2n minus 1 factorial in the denominator. And that continues to go on and on and on. If we want to talk about just the tangent line approximation, that would be here. We would stop at the linear term for a tangent line, and that's what we would have done in the past. And this is again centered at 0, so this is the Maclaurin series. One other thing that we might want to note when we are talking about sine of x and its Maclaurin series is that this is, or the Maclaurin polynomial here, we're being told to construct a 7th degree polynomial. So I want to get to degree 7. If this asked me for a polynomial for sine of x centered at x equals 0 with 5 terms, notice that I only have 4 non-zero terms here. So if it asked me for a 5th term, I would probably have to, well, I would definitely have to add x to the 9th over 9 factorial. That would be something that I would have to continue to add there in order to get a 5th term. So one thing that you have to notice is the difference between when they ask for a degree and the number of terms. Okay, so let's write this using summation notation. So the sum from n equals, let's actually go n equals 1 to infinity. So this is, I actually missed something when I was doing the Taylor series here. I need a little alternating term because I have positives and negatives going on. So this is kind of important when I am looking at which n I need to pick. Should I put n or should I put n minus 1? So if I'm starting at 1, my first term is positive and my second term is negative. And if I look, when I substitute in 1 for n, I get a negative first term and then a positive, and then it's x for that. And then I would get a positive second term, and then I'd get x cubed over 3 factorial. So this is not good. So I might have to change that to n minus 1 or n plus 1 or something where I write it down so my first term is positive and my second term is negative. So when I write this summation, n equals 1 to infinity of negative 1 to the n minus 1 times x to the 2n minus 1 over 2n minus 1 factorial. And you're always going to want to, if you're writing your summation, make sure that everything works out. So in this particular case, if I sub in 1, I have a positive term. I get x to the 1 over 1 factorial. And that's good. That's what I want. Then the second term is going to be positive. Or I'm sorry, it'll be negative. Yeah, because n equals 2. So I'll get negative 1 times x to the 3 over 3 factorial. And that's exactly what I want. So you just kind of got to play around with it and make sure it works. Interval of convergence, I will once again use the ratio test. So the limit as n approaches infinity of the negatives don't really matter because it's an absolute convergence test. So this ends up being x to the 2n plus 1, x to the 2n plus 1, and x to the 2n minus 1 in the numerator and denominator. So that ends up being x squared in the numerator. And in the denominator, I get 2n plus 1 times 2n. Again, when I do this, what I find out is this limit ends up being 0. And that means that it has absolute convergence for all values of x. I know that was a lot of math there, but I end up getting an interval of convergence being negative infinity to infinity. Okay, construct a fourth degree polynomial for cosine. So if I'm constructing a fourth degree polynomial for cosine, notice that it's centered at x equals pi over 4. So that means that I'm going to have to be pretty careful here. So if I'm taking a look at this, cosine of pi over 4 is root 2 over 2. So cosine of x is approximately root 2 over 2 plus, now if I'm taking a look at f prime, that's negative sine. So negative sine of pi over 4 is negative root 2 over 2 times x minus pi over 4. I'm going to definitely have to move all of these a little bit over because we're going to run out of room. And then negative cosine, again, negative cosine is going to be negative root 2 over 2 times x minus pi over 4 squared over 2 factorial plus root 2 over 2. And the reason why it's plus is this derivative ends up being positive. So root 2 over 2 times x minus pi over 4 cubed over 3 factorial. 2 factorial is 2, so I don't really need the factorial if I don't want. And then I need one more term, and it's back to this one, which is positive. So root 2 over 2, x minus pi over 4 to the 4th power over 4 factorial. That's really annoying. And so that's one thing that you might want to think about when you're doing approximations is this is not very fun. And when we were doing tangent line approximations, we thought the same thing. We wanted to find some value that's easy to calculate all the time. Now, while cosine and sine of pi over 4 are easy to calculate, this polynomial gets really nasty really fast. Whereas when I did the sine calculation centered at 0, it converged for all values of x, and it was a really clean function. So there's probably not a need to do this one centered at pi over 4. It makes all of these more complicated. And there are a ton more terms because cosine and sine are both non-zero values all the time at pi over 4. So this actually kind of becomes a little bit annoying. In the interest of time, I'm not going to explain why everything works out the way it is for this problem, but you need this -1 to the power to end up going from positive to then 2 negatives in a row, then 2 positives in a row, then 2 negatives in a row, then 2 positives in a row. So there are actually numerous ways that you can make this exponent, but I think the easiest way is cosine of pi n over 2 minus sine of pi n over 2, which is an awful exponent. But really what this problem is meant to do is show you that approximations are not all made equal. And so problem 3, this is not a great approximation to use. It works out perfectly. If you found the interval of convergence, it would be negative infinity to infinity. If you typed in this polynomial going off to infinity, it would perfectly match cosine of x. However, there are way more efficient ways to do it, namely by centering it at 0 in this particular case, because it goes from negative infinity to infinity. Sine and cosine work out really, really well for Taylor series centered at 0.